G'day. Today we're going to be looking at temperature and thermal expansion. This is the first topic for week 9 of the course. As usual, I'm going to jump over to the PowerPoint. We'll watch the slideshow for a bit, but I may jump back and forth depending on if there are some examples. I can't quite recall if I've got any in the first half. So the first half we'll be looking at temperature. What is temperature? How do we define it? How do we measure it? Then we'll move on to thermal expansion in the second video. And as usual, I will finish with a video of questions and problems and walk you through how to solve those. There are quite a few questions, so the third video will probably be slightly longer than normal for this lecture. Right, so the topics for this lecture are to relate mass and number of atoms. So we're still thinking about the idea that everything's made of atoms, and we want to be able to think about what how many of them there are in any substance. I want to understand what temperature represents, explain how temperature scales are constructed, convert between temperature scales, relate changes in the size of objects to changes in their temperature. So that's moving into the thermal expansion part of the lecture. And we want to compute stress on an object due to thermal expansion. So we've already met stress, and now we're going to bring it into thermal expansion and talk about that. So to start with, you already know temperature. You should all be familiar with the concept of temperature because frankly, you can't really go a day in your life without being aware of the temperature. It is either too hot or too cold, or it might be just right. But regardless, we are always perceiving temperature in terms of how comfortable we are with the surrounding environment. We also understand what it means to melt, to boil, to cook, to burn. These all involve temperature changes of other objects. Or ourselves, unfortunately, sometimes. And this is just because it's part of our daily life. We live in an environment where there is temperature. Temperature is just a property of everything in the universe, whether it's cold, hot, or something that we find comfortable. There is always a temperature to every object. So because it's just everywhere all the time, we are obviously familiar with it. But what does it really mean on a scientific sense? That's what we're going to be looking at as we go through these next few lectures. So to start with, just a reminder that everything is made of atoms. So hopefully by now most of you are used to this. We're told this from quite a young age in modern day civilization. We're told that everything is made of atoms. So it shouldn't really be a surprise. But back before atoms were really believed, they thought they were just a useful tool to describe how things worked rather than actually a real thing. But this guy Brown, he discovered that pollen atoms were dancing when they sat on water. I'm going to mute that. I don't know if that came through, but I didn't like that noise. Right, so this is just a little video clip of some pollen grains sitting on water. And you can see that they're just jiggling around. And this is exactly what the botanist, or biologist found when he observed those pollen grains on water, not those exact ones, but some pollen grains on water. And he saw that they were jiggling, they were moving. He thought, maybe pollen is alive. And so he tried it with coal dust, which he knew wouldn't be alive, and that jiggled too. So he went, okay, that's just some weird phenomenon, something about small things on water and they jiggle, and he left it there. He didn't bother with it anymore. And it wasn't until Albert Einstein came along a bit later, and he said, hey, that thing you found, that actually is proof of atoms. Because what's happening is that every one of those pollen grains is being constantly bombarded by water molecules, because the water is made of molecules, made of smaller things. And so as they move around, they collide with those pollen grains, which are big enough for us to see. We can't see the water molecules, but we can see the pollen grains. And when the water molecules collide with the pollen grains, then if enough of them happen to hit it in one direction for a moment, it'll jiggle away from those, and then some might get hit back the other way and it'll jiggle back. So it doesn't really have any great amount of motion, but just occasionally there'll be slightly more molecules hitting it from one side than there are from the other, and it'll have a net force and it'll move. And so Albert Einstein used this Brownian motion as proof of the existence of atoms. So with that out of the way, everyone could get down to the business of really defining these properties of these atoms. And at that point, we're dealing with really, really small things. So the mass of 1/12 of a carbon-12 atom is 1.66, all those numbers, times 10 to the minus 27 kilograms. So tiny, right? 10 to the negative 27. You got to write 26 zeros before that 1 after the decimal place. So it's not very useful for us to work in those sorts of numbers consistently. If you're writing out a whole bunch of terms, a whole bunch of properties, a whole bunch of equations, whatever you happen to be doing, if you have to write times 10 to the negative 27 on every single one of them, it becomes very tedious and very easy to make mistakes, very easy to get things wrong. So they came up with this idea of the atomic mass unit, sometimes referred to as the unified atomic mass unit. And the idea is that they just said, all right, let's take a carbon-12 atom. It's a nice, common, simple one. And we'll say 1/12 of that. So remember that carbon-12 has a mass of 12. Right? It's got 12 things. Have you guys done nuclear physics? I'm not sure. In the nucleus of a carbon-12 atom, you've got 12 protons and neutrons. And that's where all the mass of the carbon atom actually is. So by saying 1/12 of that, you're essentially saying the mass of one of those protons or neutrons. But as you will learn if you haven't yet, the mass isn't exactly the same as a free proton or a free neutron when they're in a carbon-12 atom. So that's why we stick with the carbon-12 atom, just because it's a common one, it's a good reference point. Forget all of that stuff I just said. The mass of 1/12 of a carbon-12 atom is what we defined as the atomic mass unit, and that is that value that I just said, 1.66 times 10 to the negative 27 kilograms, or 1.66 yoctograms if you want to move into those units. And as I said, it's about the mass of one proton or neutron. It's slightly less than a free proton or neutron. So it just means that we can write things in the atomic mass unit instead of in kilograms with these ridiculous scientific exponents, these 10 to the negative 27s. So as an example to show you what we mean, the density of copper is 8.9 times 10 to the 3 kilograms per cubic meter. Every copper atom has a mass of 63 U. Right? So that's the atomic mass unit, U. The question is, estimate the average density, average distance between the center of neighboring copper atoms and a piece of pure copper. All right, so this is tying in this atomic mass unit, but also getting us to think about the physical structure of things that are made of atoms. So I will jump to the document camera for this one. So what we're looking at is copper. So we've been told we've got copper, and it's got a density of 8.9 times 10 to the 3 kilograms per cubic meter. And we're also told that the mass of each copper atom, so I'll go mass of a copper atom, is equal to 63 U. And the question is, what's the distance between each neighboring copper atom? So we've got to make a few assumptions to do this. We haven't been told anything about the actual structure of copper when it's in its metallic form, when it's in its solid form. So we're going to make an assumption. What we're going to do is we're going to say, all right, well, let's just pretend it's a really simple grid pattern, all right? So we get 4 and these bond to each other, all right? And then they'll bond with ones that are a little further back, all right? And so if you have 8 of them, then you get this cube. Right, so we get this cube of 8 copper atoms. So we're going to assume that they look like this. If you went into some chemistry discussions, you could figure out the actual geometric structure, and then you could figure out the distance based on that. But just for simplicity, for the sake of argument, we're going to take this as being the nature of our thing, of our copper solid. And so that would mean that every one of these would then bond to more atoms. Right, and so we would get just this continuing lattice of all of these atoms. So you just keep adding more and more on, right? And that's how the solid would be built up, is by adding these atoms in. So we're going to assume that that's what it looks like, and that everywhere these are all the same distance apart because they're all copper atoms. And so the question is, what is this distance here? What's the distance from one atom to the next one? That pink doesn't show through very well, but hopefully you can tell that. Right, so we're trying to figure that out. And we've been given this information. So what we're going to do is we're going to say, all right, well, let's imagine we've got a whole cubic meter. All right, so we've got one whole cubic meter of copper. All right, so here's our 1 cubic meter. So it's 1 meter in every dimension. And that whole thing is just made of copper. We know that that weighs 8.9 times 10 to the 3 kilograms. So this has a mass of 8,900 kilograms. That's how much mass there is in this 1 cubic meter block. So the reason I chose a cubic meter is because our density is obviously kilograms per cubic meter, and it makes this calculation very easy. We've now got 1 cubic meter, means the mass is exactly that density value, but in kilograms. So we've got 8,900 kilograms, and that can actually tell us how many atoms there are, because we know that each atom has a mass of 63 atomic units. Right, if each atom has a mass of 63 atomic units, then that means to figure out how many copper atoms there are. To figure out how many copper atoms there are, we just have to take 89,000 kilograms and divide it by 63U. And so that will let us, we're saying we've got this much mass and each one weighs this much mass. That'll tell us how many copper atoms there are. Obviously, they're in different units, so we need to convert them. So if you've got the printed notes, or if you're just relying on me to tell you, the previous slide told us that 1U is equal to 1.66, we'll just go with that, 2 decimal places, 3SF for now, times 10 to the negative 27 kilograms. So all we have to do is do 63 times this, and that gives us the mass of each copper atom. So the mass of 1 copper atom is equal to, I should have grabbed my calculator already for this. Here we go. So the mass of each copper atom is 1.66 e to the negative 27 times 63, which is 1.0, we'll just go 1.05 times 10 to the negative 25 kilograms. So that's how many kilograms we have per copper atom. And so now we can do 8,900 kilograms divided by this to tell us how many actual atoms there are. So 8,900 divided by that value gives us 8.51 times 10 to the 28 atoms. So there are 8.51 times 10 to the 28 atoms. So now we know how many atoms there are in this block. But now we've got to go from that knowledge to this distance value. And this just takes a little bit of geometric reasoning, just thinking about the situation. If we have this kind of grid for this whole thing, now keep in mind this is very much not to scale, since we've got this many atoms, I can't draw them all. But if you imagine that we've got one atom here, the next one here, the next one here, all the way along, all the way along that edge, let's say we have n atoms. Right? And each of those atoms is separated by a distance d. Then going this way, we're going to have another n, right? Because we said that d is the same everywhere. So if each of these atoms is separated by d as well, then that means that along this edge we have another n atoms. And then all the way up here we've got another n atoms. So we've got n times n times n. If you've got a grid of things where there's n of them across, n of them along, and then n of them up, you're going to have n cubed atoms. All right? So we know that if this is made up of this kind of grid, which is our assumption, then we're going to have n cubed atoms, where n is how many is along each side. And we've just said that we have this many atoms. All right? So that means that n cubed is equal to this total number of atoms. All right? So we have n cubed is equal to 8.51 times 10 to the 28. So now you just have to do the cube root. So if you're familiar with scientific calculators, they all should have a cube root function. So we do the cube root of that, and it tells us that we have, it hasn't given it to me in scientific notation, 1, 2. I think I just did a very quick count, 4.40. 4.40 times 10 to the 9. And that makes sense because 3 9s are 27 and 4. Yeah, okay. So that's how many are along each side. So each side, each one length of this 1 meter has 4.4 times 10 to the 9 atoms. So that means that we can now figure out this distance, because the spacing between all of those has to be equal to 1 meter. Now, technically there's one less space than there are the number of atoms, but because of the number of atoms, taking one off it is not going to help at all. So we're going to ignore the fact that we're actually looking at n-1, because n-1 is still going to be written the same unless you're going out to 10 significant figures. So what we've got is 1 meter is equal to 4.40 times 10 to the 9 times d. So it's just geometric reasoning once we got to this point. Once we figured out the number of atoms, rather, at this point, once we figured that out, it's just geometric reasoning to say, well, we've got n cubed atoms, therefore we've got this many along each side, and therefore the distance is this much. So we can just rearrange that for d, for the distance, and obviously then you're going to get 1 meter divided by this many, right? So that's going to go into the bottom of the fraction over this side, and you get out that d is equal to 2.27 times 10 to the minus 10 meters. Right? And those of you that are familiar with nanometers will know that a nanometer is 10 to the negative 9, so it equals 0.227 nanometers if you want to go into those units. And so that's the distance from one atom to the next. Obviously, we made some assumptions there. As I said, you could become more accurate by going and figuring out the exact structure and determining whether it is anything like that. I'm not going to tell you whether it is or not, because for the sake of argument, we've made an assumption and we're just going to stick with it. So that's our example. As usual, solution is in the slideshow. So we've got this idea that everything is made of atoms. We've got a new atomic mass unit just so that we can talk about it more simply and not have to deal with scientific exponents everywhere all the time. But obviously we will come back to that when we're comparing to densities and things. So the next question is, what is temperature then? If everything's made of all these atoms, these tiny little things, what is temperature when we talk about that? What does it mean for something to be hot? It turns out that temperature is actually just the kinetic energy of all of those particles, the things that make up that object. That's all temperature is. We all know kinetic energy. We're familiar with it because we look at kinetic energy of larger bodies. And now we're saying that for all of those little atoms, those molecules, whatever the object is made out of, or the substance is made out of, they all have some kinetic energy. They're all moving around. Then that kinetic energy is what we mean by temperature. And so in that sense, when we're talking about temperature, we're actually talking about energy. We're going to come more into this discussion a bit later on, but for now you just need to agree that that's what we mean by temperature. We'll talk about how it transfers and what it means in terms of statistical distributions and things later on. So that's what temperature is. So the average kinetic energy of each particle, so average kinetic energy of all the particles, rather, is how we define temperature. As I said, the statistical distribution that we'll come back to means each one can have a bit less or a bit more energy. Right? They don't all have exactly the same for one object to be at a certain temperature. It's an average of all of them. We will talk more about all of that. We'll also talk more about heat. We're going to come back to heat. Thermal energy is what we call the temperature, because it is energy that the particles have that we perceive as a temperature, as some kind of energy, some kind of hot or cold, depending on whether it has more or less. So that has to be able to transfer from one object to another, and that transfer of heat energy or thermal energy is heat. I shouldn't have said heat energy, that's bad use of the language. Right? Heat is only the transfer of that thermal energy. When something has a temperature, which everything in the universe has, when something has some temperature, that tells us how much internal energy. Again, we'll come back to these terms later. It'll all hopefully make sense, but it's a big picture thing that we'll build up to. So it has some energy in the particles, and if that energy is transferred to another object, we call that transfer the heat. So we're going to come back to that again as well. And finally, the most useful way to think of temperature is as a comparative property. So temperature is a measure of how much energy all the particles in a substance have, And if we say that this thing has a higher temperature than this thing, then what we're saying is that the first thing has more energy per particle than the second thing, right? That's what we're actually saying. That's why temperature is useful, because it can tell us which of these two objects that we have to consider actually has more energy, thermal energy, the kinetic energy of each little particle per particle compared to the other one, right? So that's what we're talking about. Just noticed I've written a question on this slide. Is there still energy moving between two objects at thermal equilibrium? We are going to talk about thermal equilibrium in a moment, so that'll make more sense when we look at that. And now this slide is almost one you can forget a little bit. Actually, no, I shouldn't say that. I want you to know what a state function is. I want you to be aware of the term, but we don't really use it or come back to it too much. It's more just it's a scientific term that allows us to continue our discussions knowing that certain things are true. So the state functions are properties of a system that are true, well, that are independent of how you got there, right? So if you've got a bowl of water, then that could have been steam that you condensed and directed to form into a bowl. Right, so you could have condensed steam or even just air out of the atmosphere, and you could have condensed it and got it into a bowl, or you could have taken a block of ice and you could have put it in a bowl and then waited for it to melt, or you could have just gone to a river and grabbed a bunch of water that was already water. So there are different ways for you to end up with this bowl of water, but the point is that no matter how you got there, if that bowl of water is identical, then the mass is going to be the same. It doesn't care about where it came from. The mass is independent of its history, right? It doesn't care about the history of that water. Same thing with the energy in that water. And these other terms that you're not going to need to know. You don't need to know at this point. We will talk about some of them. We don't need to know at this point entropy. We will learn it. We've already met pressure, temperature. We're talking about now. You know what volume is. So those things we will or have met. And all of them don't care about the history of that water. Once it's a bowl of water, that's all that matters. Doesn't matter where it came from before that. The other ones that you're not really going to look at are chemical composition, specific volume, fugacity. You are aware of altitude and particle number, but we're not going to bring them directly into it. So that's the idea of a state function. It's just a way of us to communicate that the history of this object doesn't matter. Right? Where it came from is irrelevant. Once it is in this form, in this state that we're looking at, then we know these properties, and it doesn't actually, the history is not going to change that. So it's just a state function. Homeopathy is obviously based on the idea that it does have a memory, it does have a history. And so this, in a sense, in one word, is our rebuttal for that. We've got state functions, which mean the history doesn't actually matter. So we've got temperature, we've said what it is, we've talked about what it means in terms of the particles themselves having kinetic energy. So how do we measure it? What do we actually do? We've said this thing's hotter than this thing, but what does that mean? How are we putting values on this? Well, without really defining it, we can just use that comparative property to come up with a temperature scale. Right? So we can just say, well, this thing will define this temperature as a number, and this other temperature as a number, and come up with a scale between them. So rather than going down and finding out the energy and using some function of that, we're just going to say, let's just keep it comparative. Let's find two reference points and fit a straight line, because that's all you need, right? You need two reference points, and then you can draw a straight line. So thermometers were designed to do that. They use thermal expansion, which we're going to talk about more in the second half of this lecture. But they use thermal expansion to measure the comparative temperature of objects. So we'll come back to that soon. So coming up with a temperature scale. Back in 1724, around about, Daniel Gabriel Fahrenheit set up his temperature scale. Now, I just said we only need 2 points to fit a straight line, but he overcompensated and he fit 3 points, which only serves to confuse things, especially when one of them is the internal body temperature, which is A, inconsistent, and B, well, no, just inconsistent, right? It's inconsistent. So we've got a slurry of ice, water, and ammonium chloride, and he said, right, we'll make that 0 degrees Celsius. He said that we'll make the freezing point of water 32 degrees, and we'll call internal body temperature 96 degrees Fahrenheit. Now, to get all three of those to fit into a straight line, he would have had to play with all three at once, right? So the point of having two points to fit a straight line is that you choose 2 points and then you just fit a straight line to them. If you've got three, then you've got to actually define one of them based on the other two anyway. So he was essentially using two, but he was defining three at once for some reason. Later on, after he had established it, it was fixed to have 180 degrees Fahrenheit between freezing and boiling points of water. So freezing was still 32-ish, and then it went up to 180 degrees from there to get to the boiling point of water. And it was pretty common for quite a while, for a couple of hundred years, up until the 1970s when Celsius became more popular. Mostly more popular. Still obviously used as a weather temperature around the world. There's very little scientific discussion in Fahrenheit. So this guy, Anders Celsius, he came up with the Celsius scale. While he was alive, it was called the centigrade scale. He didn't name it after himself. I can't make that statement for Fahrenheit. I don't know whether he named it after himself or not, but Celsius didn't. He called it the centigrade scale. The centi coming from 100, same way as percent, right? Cent meaning 100. Centigrade is just a gradient, a scale of 100. And so what he did was he said, right, let's just take our 2 points, and two common points or easy reference points are boiling of water and freezing of water. Right, so he'll set those to his 0 and his 100. And that's a good idea, right? To get those two common substance, common temperatures, water freezing, water boiling, easy. So that was a good idea, but unfortunately he did it back to front, and he called boiling 0 degrees and freezing 100 degrees, and it got higher as you got colder. So that was his interpretation of it. I'm not sure why. It didn't stick, obviously, but that was how he originally defined it. About a year after he died, Carl Linnaeus said, well, that's just dumb. Let's swap it around. And so he just flipped it. He said, right now, freezes at 0, boils at 100. And that was the Celsius scale. They also renamed it to Celsius in honor of Celsius's idea of having a 100-step scale from water freezing to boiling, which, as I said, was a good idea. He just had it back to front from any kind of useful sense. From Fahrenheit to Celsius, you can convert temperatures fairly easily. It is 9/5 of the Celsius temperature plus 32 degrees will give you the Fahrenheit scale. So the plus 32 is just because the freezing point of water is 0 on Celsius, but it's 32 on Fahrenheit. So we need to adjust by that much. And the 9/5 is just the relative step size of each of the scales. Obviously, you can rearrange that to go from Fahrenheit back into Celsius. Then, far more recently than the other guys, Lord Kelvin, who at the time was known as William Thomson, he wrote a paper explaining why we should come up with an absolute temperature scale. Because if temperature is the energy of the particles that make up substances, then you could cool something down, just continually take energy away from it, cool it down until the particles have no energy. Right? And when they've got absolutely no energy, it's impossible to get colder because you can't get less than nothing. So that should be our 0, not where water freezes. That's just some value that we happen to like because we deal with water so much. But there's no real reason that should be called 0. If we go and set absolute 0 there to when things have absolutely no energy at all, none of this temperature at all, then we call that 0. That makes our scale make sense. We've now got no energy, and we go all the way up to more positive values for energy. And he kept the step size the same as Celsius. He liked the idea of there being 100 between water freezing and boiling, which, it's fine for him to keep that and not the other part. It does raise some questions. Why, if we're not caring about the freezing of water being a special point or the boiling of water being a special point, then why keep the step size to be 100 there? There's no real reason except that it makes all of our calculations very easy to convert from Celsius to Kelvin. If it was some other abstract value, it would be a lot harder to deal with. So it is easier to shift into Kelvin because of that consistency with the Celsius step size. An important note, although it's important but it's not critical, is that temperatures in Kelvin are not degrees. We don't say degrees Kelvin, we just say Kelvin. A Kelvin is the step size, a degree Celsius is a step size, right? So it's not degrees Kelvin. So if we do that, we set our 0 Kelvin to be our absolute 0. Then we can set we find that the triple point of water, which is something we haven't really met yet, I don't think, but it's essentially the freezing point of water, is 273.16 Kelvin. So that becomes the freezing point of water. So the conversion from Celsius to Kelvin is very easy. We just add 273.16 to our Celsius temperature. That gives us Kelvin, or we take off 273.16, and that gives us the Kelvin back from the Celsius back from the Kelvin. So it's just adding or subtracting that value. That's all we have to do to get Kelvin into Celsius and vice versa. So some interesting temperatures. There's no need to memorize any of these, but it does give you a reference scale for temperatures. We're used to just everyday temperatures where things generally range in that 0 to 100 Celsius because that's what we deal with. We deal with things freezing. Obviously, it does get a little bit lower than that in some places in the world, but here in New Zealand, we generally don't get too much below that, maybe a degree or two, unless you're going up mountains and things. But anyway, I'm getting sidetracked. So that 0 to 100 or even 0 to sort of 40 or 50 is a pretty common range of temperatures for us to deal with. When we have specialized utensils like an oven in your home, you can get up to a couple of 100 degrees Celsius. So we're familiar with those sorts of temperatures, but obviously in the universe, there's a much wider range of temperatures. These are just some example values, so feel free to pause the video and have a read through those, but you'll see the lowest one. I'm just going to point out two, and that is, actually I'll do three. The lowest temperature produced in a laboratory. So in a physics lab, somewhere in the world, I don't know if it was physics, but in a lab somewhere in the world, they got down to 100 picokelvin. So pico, if you remember your SI, your prefixes, pico is 10 to the negative 12. They got down to 100 times 10 to the negative 12 Kelvin. So that's how cold they made something in a lab. And on the other end of that spectrum, the highest temperature produced in a lab is 4 trillion Kelvin. 4 trillion. And just for comparison, 10 times 10 to the 13 Kelvin was the temperature just after the Big Bang, 0.000100, did I say that right? 3 O's, 1 seconds after the Big Bang. So that's just a quick reference. As I said, feel free to read through all of those. As I said, 2 temperature points, 2 reference points, choose how many steps between them. There's a temperature scale. We've got Fahrenheit, we've got Celsius, we've got Kelvin. What other temperature scales might be interesting? This is just a rhetorical question for you, rhetorical from my perspective in the sense that I'm not going to hear your answers, but you should have an actual think about it. Do come up with one if you want, right? Think about other ways that might be interesting, other things that might be fun. There are other temperature scales, there are others that have been proposed. None have really caught on, but there are certainly other options. So do feel free to have a look around online or just come up with some yourself. And now to finish this half of the lecture, I'm just going to bring in the 0th law of thermodynamics. This is the 0th law because the first, second, so on had been come up with already. They'd already come up with the first and second laws. And then they said, well, this is kind of more fundamental. This is just, it just is a true thing. Right? And so rather than renaming the other ones, they just said, well, we'll just call this the 0th. Right? It's really important. We'll just chuck it in front and call it 0. So the idea is just that if you've got 2 objects that are in thermal equilibrium with each other, with a third body, then they're also in thermal equilibrium with themselves, with each other. So actually, I'll just jump to my document camera again for a moment. So we'll jump to the document camera. And the idea is just this. You've got some object here, and it's in contact with this object, and that is in contact with this object. So this is object A, B, and C. And what we're saying is that the temperature of A and the temperature of B are the same. That's what thermal equilibrium means. Thermal equilibrium just means that they have the same temperature. And remember, temperature is talking about the average kinetic energy of each particle that makes up the object. So the average temperature, average kinetic energy of these particles is the same as the average ones of these particles. Then that means that they have the same temperature, and that means they're in thermal equilibrium. That's just what we call it. So we're saying that's the same. And then we're saying these two are also touching, and they're also the same. They also have the same thermal equilibrium. the same equilibrium, not making any sense now, the same temperature, they're at thermal equilibrium. And if that's true, then it means that the temperature of object A and the temperature of object C are the same. It's basically just saying that once temperature is defined and you say two things at the same temperature, then if a third thing is at the same temperature, then obviously it's the same temperature as the first thing. Right? So it's almost common sense. It almost just makes sense without me needing to tell you it. But because it's so important, we wanted to state it. Not like I was part of the decision, but we wanted to state it as a formal law to be very clear about it. Right? And if two things aren't in thermal equilibrium, then they will transfer thermal energy between each other. Right? Remember we talked about heat. Heat is the flow of thermal energy. We're going to talk more about that in another lecture. But they will transfer thermal energy until they are at thermal equilibrium. So they do adjust to each other's contact if they are, to each other's energies if they are there. They will come to one average kinetic energy. So that is the end of the first lecture for this, for the first half of this first lecture for this week. So I will be doing another one shortly, and you'll see that come up. And then, as I said, there'll be some questions as well at the end.